Good morning to all of you. In previous session, we have seen one of the property of Z transform, that is linearity property, and we have solved one example where we identified the Z transform by applying the linearity property. In today's session, we will see one more example where we will be using linearity property to obtain the Z transform of the given discrete time signal. So in this example, again we have to determine the Z transform of the signals. Okay, so there are two different signals, that is x of n is equals to cos omega 0 n into u of n, and second signal is x of n into sin omega 0 n into u of n. So these are the two different discrete time signals given, so we have to identify the Z transform of these signals. Okay, but before proceeding to the solution of this example, all of you are aware about the Euler's identity, right? So as per the Euler's identity, we know that e to the power j omega can be represented as cos omega plus j sin omega, and even we know that e to the power minus j omega is equals to cos omega minus j sin omega, right? So this is as per the Euler's identity. So if I want to write down the equation for cos omega, right? So cos omega will be simply 1 by 2 e to the power j omega plus e to the power minus j omega, right? So why? Because e to the power j omega is nothing but cos omega plus j sin omega, and e to the power minus j omega will be cos omega minus j sin omega. So this j sin omega will be 0, right? Because plus minus sign are there. So it will be 2 cos omega, and to cancel that 2 here in multiplication there is value 1 by 2. Okay, so 2 will get cancelled, only cos omega will remain, right? So similarly, this sin omega can be represented as 1 upon 2j, right? E to the power j omega minus e to the power minus j omega, right? Because again e to the power j omega is cos omega plus j sin omega, and this e to the power minus j omega will be cos omega minus j sin omega. So as negative sign is there, so this minus cos omega plus cos omega will be 0, and this minus minus plus sign will be there, so it will be 2j sin omega, and to cancel that 2j we have multiplied it with 1 upon 2j, so we'll get only sin omega there, right? So by applying this Euler's identity, you can rewrite the given signals, okay, given discrete time signals. Okay, so let's try to solve this example where two different signals are there. We'll initially try to identify the Z transform of the first given signal. Okay, it is given as x of n is equals to the given signal, so it is cos omega 0 n into u of n. Okay, so again by using the Euler's identity, the signal x of n can be expressed as, so how you can represent it as, so you can represent it as this x of n can be written as, in place of cos omega 0 n you can use this 1 by 2 in place of omega 0 n, so it will be 1 by 2 e to the power j omega 0 n plus e to the power minus j omega 0 n. Okay, so you can simply write it as 1 by 2 e to the power j omega 0 n, right, plus 1 by 2 e to the power minus j omega 0 n into u of n. So in place of cos omega 0 n we have substituted this value, right? So again by using according to the linearity property, or basically initially you can separate this signal as x of n is equals to, I can write 1 by 2 e to the power j omega 0 n into u of n, right, plus 1 by 2 e to the power minus j omega 0 n into u of n. Okay, so I multiplied this 1 by 2. Sorry, here this 1 by 2 should not be there, right, because bracket has been taken here. So 1 by 2 in bracket e to the power j omega 0 n plus e to the power minus j omega 0 n into u of n. So 1 by 2 has been multiplied inside, while similarly u of n has been multiplied. So as per linearity property, we can say that this is your x1 of n, small x1 of n, this is x2 of n, right, and this 1 by 2 1 by 2 will be your constant a1 and a2, sharing same value. Okay, so as per linearity property, okay, we can say that this x1 of x of n has the z transform represented as capital X of z, and the Z transform as per this linearity property will be the linear combination of these signals respective Z transform. Okay, that means 1 by 2 multiplied by the Z transform of e to the power j omega 0 n into u of n plus 1 by 2 Z transform of e to the power minus j omega 0 n into u of n. Okay. So this is how you will be identifying their respective Z transforms. Okay. So I will rewrite this equation, last equation here, that is x of z is equals to what we have here, that is 1 by 2 the Z transform of, that is that e to the power j omega 0 n to the power j omega 0 n into u of n plus 1 by 2 Z transform of e to the power minus j omega 0 n into u of n. Okay, so as per the formula of Z transform, so it will be 1 by 2 summation n is equals to minus infinity to infinity e to the power j omega 0 n into u of n into z to the power minus n. Okay, so in place of this Z transform, we have substituted the Z transform formula. So we are taking the Z transform of e to the power j omega 0 n u of n into, it will be the z to the power minus n. Similarly 1 by 2 again summation n is equals to minus infinity to infinity, right, e to the power minus j omega 0 n into u of n into z to the power minus n. Okay, so again u of n is there, right, in both signals, so you can restrict the limits. Instead of minus infinity to infinity, you can eliminate the negative values and you can take it as 0 to infinity. So 1 by 2 summation n is equals to 0 to infinity e to the power j omega 0 n into z to the power minus n plus 1 by 2 summation again n is equals to 0 to infinity. We eliminated negative values of n from both summations, and in place of u of n you have substituted value 1. Okay, so e to the power minus j omega 0 n into z to the power minus n. So you can take again n common. Okay, so n is equals to 0 to infinity, so it will be e to the power omega 0, sorry, j omega 0 into z inverse raised to the power n. Okay, plus 1 by 2 the summation n is equals to 0 to infinity, it will be e to the power minus j omega 0 z inverse raised to the power n. Okay, and as per that infinite geometric series, we can simplify it as what, 1 by 2. Okay, 1 by 2 into 1 upon 1 minus this e to the power j omega 0 z inverse, right, plus 1 by 2 again 1 upon 1 minus e to the power minus j omega 0 z inverse, right, provided that this mod z inverse e to the power j omega 0 should be less than 1. Similarly this mod e to the power minus j omega 0 z inverse should be less than 1. Okay, so in this case it will be mod z what greater than e to the power j omega 0 and in this case it will be mod z greater than e to the power minus j omega 0. So this will be the ROC of these individual terms. But we know that this e to the power j omega 0 is approximately 1. Similarly, e to the power minus j omega 0 is also 1. Okay, if you evaluate for the various values of omega here. Right, so you can take it as simply mod z greater than 1, and here also you can take it as mod z greater than 1. So the overall ROC of the given signal will be simply mod z greater than 1. Okay. So this is the required Z transform. What will be the required Z transform? X of Z is equals to 1 by 2. You can also take this 1 by 2 common, right, if you want. So 1 by 2 into 1 upon 1 minus e to the power j omega 0 into Z inverse, right, plus 1 by 2 into 1 upon 1 minus e to the power minus j omega 0 to Z inverse. Okay, and with ROC mod z greater than 1. Okay, so this is the required Z transform of the given signal. Given signal was x of n is equals to cos omega 0 n into u of n. Okay, this was the given signal and its Z transform is this one. Even you can simplify these terms by substituting the values of e to the power j omega 0. You can substitute here cos omega 0 plus j sin omega 0. Here also you can substitute the value cos omega 0 minus j sin omega 0, right, and you can simplify it and you can represent it in terms of cos or sin functions, right, but there is no need, or you can again simplify it. Okay, so this is the required rate transform of x of n. Similarly, you can identify it for the second, that is x of n is equals to sin omega 0 n into u of n. Okay, so second equation you are given as x of n is equals to sin omega 0 n into u of n. Okay, so again in place of sin omega 0 n you can substitute the value 1 upon 2j. Okay, so 1 upon 2j is cos omega 0 n minus what, sorry, not cos omega 0 n, 1 upon 2j into in bracket e to the power j omega 0 n minus e to the power minus j omega 0 n. Okay, by saying this as per this Euler's identity. Okay, sin omega is 1 upon 2j e to the power j omega minus e to the power minus j omega. Okay, so in place of omega there is omega 0 n, so it will be e to the power j omega 0 n minus e to the power minus j omega 0. Okay, and this u of n will be as it is, right. So again you can rewrite this signal x of n as 1 upon 2j e to the power j omega 0 n into u of n minus 1 upon 2j to the power minus j omega 0 n into u of n. So again, as per linearity property, you can take the z transform of x of n as x of z. You can take this 1 by 2j as constant a1 and you will identify the z transform e to the power j omega 0 n u of n, similarly minus 1 upon 2j z transform of e to the power minus j omega 0 n into u of n. Okay, so again I will rewrite that equation, that is x of z is equals to, what is the equation here, 1 upon 2j z transform of e to the power j omega 0 n into u of n minus 1 upon 2j z transform of e to the power minus j omega 0 n into u of n. So if I am applying the z transform formula here, so it will be 1 upon 2j summation n is equals to minus infinity to infinity e to the power j omega 0 n into u of n into z to the power minus n minus 1 upon 2j. Again summation n is equals to minus infinity to infinity. It will be again e to the power minus j omega 0 n into u of n into z to the power minus n. Okay. So again you can eliminate the negative values of n. You can take this summation limit 0 to infinity. So this u of n can be replaced with 1 for those values in both cases. So it will be 1 upon 2j summation n is equals to 0 to infinity e to the power j omega 0 n into z to the power minus n minus 1 upon 2j summation n is equals to minus infinity to infinity e to the power minus j omega 0 n z to the power minus n. Okay. So again 1 upon 2j summation n is equals to 0 to infinity. Again you can take n common, so it will be e to the power j omega 0 into z inverse whole to the power n minus 1 upon 2j summation n is equals to 0 to infinity here, right? So 0 to infinity e to the power minus j omega 0 z inverse raised to the power n, right? So the overall Z transform will be simply x of z 1 upon 2j 1 upon 1 minus e to the power j omega 0 z inverse, right? Minus 1 upon 2j 1 upon 1 minus e to the power minus j omega 0 z inverse. Okay. Again in this case this conditions on ROC will be this what mod e to the power j omega 0 z inverse should be less than 1 for first term, and second term again mod e to the power minus j omega 0 z inverse should be less than 1. Okay. So ultimately here you can write it as what mod z is greater than e to the power j omega 0 and mod z greater than e to the power minus j omega 0. Okay. So again this e to the power j omega 0 and e to the power minus j omega 0 will be approaching to 1, so mod z will be greater than 1 and mod z greater than 1. Okay, so overall ROC will be mod z greater than 1. Okay, and the required Z transform will be this one. X of z is equals to 1 by 2j into 1 upon 1 minus e to the power j omega 0 into z inverse minus 1 by 2j 1 upon 1 minus e to the power minus j omega 0 z inverse. So again if you want to simplify it, so in place of e to the power j omega 0 you can substitute cos omega 0 plus j sin omega 0. Here you can substitute cos omega 0 minus j sin omega 0. You can subtract it and you can simplify it if required, right? So this is how you can again apply the linearity property and you can identify the Z transform of the given signal, which are in terms of cos and sine function. Here we are used the Euler's identity. So this is how you will be using the linearity property to identify the respective Z transform. Okay. So in next session we will be discussing another property of Z transform, that is time shifting property. So thank you for joining this session.